Guten Tag, microXchg. That is the extent of my German, so the rest of the talk will be in English. This is monitoring bash microservices at scale. I kind of hope your initial reaction is, that's a terrible idea. Why would you want to do that? Because this is sort of a tale of what not to do. This is the journey that we took at Weave, building a cloud-native SaaS, using as much cool new tech as we can for maximum bragging rights at places like this. So we'll talk about some of the mistakes that we made and some of the things we learned from that. First, we should talk a little bit about Weaveworks. We help you connect, monitor, and deploy containers and microservices with Weave Cloud. And in a lot of ways, Weave Cloud is similar to any other SaaS, right? The architecture that we arrived at was something like this. And particularly in the kind of top left corner there, there's users, there's authentication, it's serving some static content. It's very similar to what you would normally do when you're building a SaaS product. But as a tools company, we're given a lot of leeway to develop and dog food our own tools and try stuff out. We didn't arrive at this architecture overnight. We hardly even planned it. We're big believers in emergent architecture. Do just as little architecture as you can get away with up front, and then let it grow to fit the problem domain that you're working in. So let's talk a bit about the journey and how we got here. And in about 15 minutes, you're going to be thinking, well, this guy sucks. So let's keep in mind that sucking at something is the first step to being sort of good at something. So with that, our first failure, right out of the gate, pets. So when we started Weave Cloud, the first product we wanted to host was Scope. Scope is our visualization product. It's open source, like pretty much everything we do. And the open source product is architected something like this. We wanted to reuse as much of the code as we could. So on each host, you run a probe that collects the data, does a little bit of aggregation, sends that off to the app. The app then does the actual analysis and builds it into a graph visualization and ships that to the browser. So we wanted to mirror that as closely as we could so we could reuse some code. So our initial architecture is this. So requests come in at the top here from the interwebs. They hit our kind of load balancer, and then that eventually routes requests to something called the app mapper. So the app mapper looks and says, do I have a container running for this user? Yes or no. Start one if I don't. And that's actually just running the open source code. So this got us going really, really quickly. But it means that even if a user is not currently using the system, we're running a container for them, and we need to keep track of that. So we have very high memory usage per user. It's easy to break the service for one user. And worse than that, it's hard to monitor because you have kind of random containers that you have to keep track of. And it's hard to update. So if we want to update the version that a user is running, we have to find that container, update it manually, or via app mapper. So we needed to redesign the system. This was around September 2015. So we went away, thought about it for a couple of months, and then started building something that looked a little bit more like this. So we've split the services up based on the type of traffic. So there's different types of traffic that Scope has to handle. So there's the collection service that handles incoming data. There's the query service that does the analysis and sends it out to the browser. And there's control and pipe services, which are, you can click a button and restart a container, or you can click another one and get a shell into the container. So they handle that kind of traffic. By splitting it up in that way, it lets us scale them independently, and it gives us a sort of isolation between types of traffic. So if you get a lot of very slow query requests, then it doesn't slow down your incoming data. And they're somewhat isolated that way. But more importantly, it means that the system doesn't depend on a single container, even for a single user to have a good time. You only have to be concerned with sets of containers. Because really, we should be treating our containers like cattle, not like pets. If it gets sick, you just kill it and make a new one. So this is a lot more horizontally scalable because we've split stuff by traffic. And all those services can actually stay running the same code. They actually do run the same code. They just handle different types of traffic, which lets us develop things still quickly, but then get the benefits of monitoring Right. So things are rolling along smoothly. A couple of months. This is now June of 2016. And we hit our kind of second big fail, which is pretty classic, typos. So when we started, we were just in a single availability zone, single master Kubernetes, easiest way to get going. And we wanted to move to a multi-master Kubernetes for resiliency and things like that. But more importantly, multiple availability zone. So how do we do that? So first we have to create some new minions, spread across the 3 availability zones, add the new masters, and migrate the pods across, and then we can remove the old minions. So we're going from something like this, single availability zone, single master, pretty simple, to something like this, where we have multiple availability zones, multiple masters, and it's a lot more resilient. So the masters between them do a leader election and figure out who's in charge there. Of course, there are trade-offs with this. Inter-AZ traffic is expensive, but it gives us quite a bit more resiliency in the system. So we should talk a little bit about how our infrastructure is managed. So we're big believers in using the best tool for each job. So we use all the tools. So the base layer is Terraform, right? It manages the servers. Once you have the servers up, then Ansible does all the Linux stuff to get Kubernetes running. You can use Ansible to manage the actual servers as well, but again, the best tool for the job. Ansible is really good at the Linux stuff. Terraform is really good at managing AWS services. And then once you have Ansible done all the Linux stuff, it gets Kubernetes running, and we can use Kubernetes to actually manage the pods and the workloads that are happening. The division of this is a little bit different than your standard Kubernetes setup for various reasons. And making this change to go from single AZ to multi-AZ means quite a lot of careful usage of Terraform, targeting individual nodes to kind of shuffle stuff around in the right way, and then using Ansible once that is done to get them set up. So one of my coworkers, Tom, is typing away. He's doing his thing, doing the Terraform. Yep, we'll delete those nodes, we'll create those nodes, and that was about the time we had to reset this counter in the office, which is days since we deleted all of production. 8th of December 2016, the incident. So this was 0, so we put this next to his desk. And it's not really all of production, right? It's just all the servers. It's fine. We didn't really lose any user data, so we just stopped accepting new data, which was good. So this is what we're going to call a learning opportunity. So what did we learn? So first we learned we can bring up a new production cluster in about 20 minutes if we type really fast in a panic. But more importantly, this isn't a good plan, right? You can't rely on people watching things constantly to catch errors, or on not making mistakes, or on necessarily double-checking what they're doing, or knowing how to double-check what they're doing. We can't rely on eternal moral vigilance to stop things from failing in our systems. We need to provide people with safe tools instead. People make mistakes, right? Dangerous things should be hard to do, especially accidentally. You need to help them double check, right? It's like the nuclear switch. You got to lift the glass cover, and then you can fire the bombs. You can't just like tweet angrily. Well, it shouldn't be complicated, right? Safe tools are simple tools. You need to help them be simple. So one of the tools that we've written from this, and particularly from this incident, the incident, was Terraform Helper. And it's not complicated, right? It should be simple. It's just a simple bash script. It's not open source, but I'll show you how the pieces fit together. It's not a secret. I just haven't put all the pieces into one place to open source it yet. So it enforces best practices, update, plan, check, then apply on top of Terraform. And it helps people to know what they should double check, because people want to do the right thing, but it's not always easy to know what that is. Nowadays, there are other simple tools, other similar tools. Right, demo time. Okay, displays, mirror displays. All right. Hey. that big enough? Let's make it a little bigger. There we go. One or two more. Cool. Okay, so let's look at the source for Terraform helper here and just talk a little bit about that. So again, simple bash script. We're kind of enforcing some constraints on the user that are the things you need to use this tool well. So we need a specific version of Terraform because there are important changes to different versions, right? And it has 3 basic commands that you can use, right? It's not complicated. There's as few ways to use it as possible, right? There's up, down, and diff. And diff looks at what's currently running and figures out what the difference is, fairly obviously. We're going to talk about that a little bit later on. So let's look at how up works. Now, it's enforcing some best practices for us, right? It's making sure that we're up to date, that our state agrees with what's actually running. Terraform does have a thing called remote state, but we're a pretty small team. There's typically only one person working on stuff at a time, so for us it was overkill. For you it might not be. And it allows us to target things and scope things down so that you can affect as little of the system as you need to, and it should make it easy to do that. And finally, it makes you actually confirm what you're doing and double check. Okay, let's see how this actually works. So let's make a small change. So we'll have a look at our thing that defines all the virtual machines that we use. And let's... Okay, so here's our definitions for our minions. And we can see immediately that we've got a couple of safety checks defined. First off, prevent destroy, so Terraform won't let us destroy it. And then the actual EC2 safety check, which says you can't disable this via the API. But let's try and do that. So let's just say one minion. I think currently there's 3. So this will say delete all the minions. Terraform helper, up, dev. And we can then scope that down to just the infra module. So we're not going to potentially affect S3 buckets or anything like that. And I'm using dev, which is our kind of testing environment for this. So just, you don't have to feel uncomfortable. Right. So it's then making an assumption about what I want to target based on how we typically work. It's going off, checking the state, making sure that we are up to date and we know everything that's going on. Right. Give that just a second to run. Water's awesome. All right. Okay, so we immediately hit the first safety check, right? So the glass is still down on the switch. We can't destroy everything. So we've hit the prevent destroy one. So let's try and tempt a little fate in the live demo. And we'll just disable the prevent destroy so that we can see, if I were about to make a mistake, what does that look like? So we've lifted the glass case, fingers on the switch now, right? Conference Wi-Fi it'll never fail. It's good. Okay. All right. So we've hit the same thing again for some reason. That's strange. Did I? Sorry? Okay, I disabled the wrong safety switch. Sweet. If you try to make something foolproof, they'll just make a better idiot. Hey-yo. Okay. So the important thing is that really this is going to now come up with an actual plan that would do what I want, but it's going to put it right in front of me. Here we go. So it's done that. So it said, here's what I'm about to do. Are you really sure this is what you mean to do? And this is typically the stage where you say, oh, yeah, that's not what I meant, actually. Let me go back and change things. Right, let's do NO. I don't want to proceed with that plan. Okay, cool. So that's Terraform helper, right? And it makes things really safe and kind of guides you down the straight and narrow path to do things correctly. All right. Mirroring off. Cool. So a lot of the safe tools that we built have helped us arrive at this kind of pattern. It doesn't have a good acronym. If you can think of one, let me know. But it starts with a version control config of what things should look like, right? Like we just saw, that's our Terraform manifests or our Ansible playbooks or that kind of thing. And then a job that watches and alerts for diffs on those. And it should be fairly lenient with the alerting time because I still want to allow myself time to make changes to the system. It's more about catching, did I forget something? And then ideally, you want a command to idempotently fix things, right? That's the tricky bit, and to some extent, it's just a nice to have. But, you know, eternal moral vigilance isn't a plan. This is a plan, and it works pretty well. So 3 of the tools that we built that work like this are, you know, kubediff, Ansible diff, and teradiff, right? They diff their respective layer, and they turn that into metrics. So then from there, we can turn that into alerts. They're all pretty similar. Let's look at one of them. So we just saw a bit of how teradiff works. Let's look at kubediff. So kubediff is a tool for Kubernetes to show differences between running state and version control configuration, which sounds pretty much like it is. It lives here. There's some example Kubernetes manifests in the k8s directory there if you want to deploy it. And it's just a simple Python script. Some instructions on how to run it, give it a go. But really all it's doing is checking out our version control config, looking at that, looking at Kubernetes, and if the Xcode is non-zero, then it tells you there's a difference, and it tells you what the difference is. So to turn that into an actual metric and alert, we use a slightly different tool called promRun, which I think is included in the kubediff repo. And all it does really is it just takes a shell command, it's a Go app, it runs it periodically, and exposes the exit code as a Prometheus metric. So we use this for all sorts of little monitoring scripts that are can be written in Bash, Python, whatever. It's fairly agnostic. It's pretty good. promRun is excellent. It's the kind of monitoring Bash microservices, right? From there, we can get alerts. So let's kind of head towards alerts here. So fail 3. That was the second one. We're in the home stretch now. DOSing DOCKERHUB. So this took ages to debug. When we were doing a Docker pull, sometimes we would get a 500, because that's the obvious response to send when you get rate limited, is give them an internal server error. So, and like all the best bugs, it was intermittent. But we didn't have any good metrics, or really any metrics, for this connection, this client that was happening, because we said, let's get the feature working, and then we'll add some metrics. So the feature in question is part of FLUX, our continuous delivery tool, is you can give it a Kubernetes service, it looks at what images are running for that, goes off and watches the registry and says, oh, if there's a new image, let me deploy that. So it has to make a lot of calls to DockerHub to say, is there a new image available? Or what is the newest image available? So if you were going to design this API, how would you do it? Okay. Well, if you had thought of anything there, I can pretty much guarantee it's not what they've done. So how it works is, first off, you make a request to get a giant list of all the tags for the image. The response is pretty unstructured. It's just an array. There's no order. There's no metadata. There's no hope. So then once you have this giant list, you go through for every single tag, and you fetch it to find when it was created, which is fine in a this is fine sort of sense, until your image has hundreds of tags or thousands, which if you're pushing from your CI pipeline is not outrageous, really. So really this got fixed because we got metrics in, right? So that's win 3. That was the thing that really helped us fix this. We added some metrics for it and discovered, oh, this is why we've been seeing those intermittent failures. So added a cache for tags, They don't really change. We can cache them for quite a long time. That was fine. Let's talk about metrics for a little bit. And there's a quote I really like about metrics, which is, when you can measure what you're speaking about and express it in numbers, you know something about it. And it goes on, if you can't express it in numbers and you can't measure it, then you don't really know anything at all about it. But more simply, we can say what gets measured gets managed. If you're not measuring your system, you're not managing your system. And if you are measuring things, people will want to optimize it and make it better. People love to make the points go up, right? Get the latency down, that kind of stuff. But it begs the question, what should you monitor? Right? So we aim to monitor 3 key metrics for every service, and these do have a good acronym: rate, errors, and duration. So it's the RED method. So the rate is how many requests are hitting the system. Errors is how many of those are errors. And duration is how long are the requests taking to go through the system. And it's the baseline that we think you should be measuring. There's also the USE acronym, USE, but that's focused on a bit of a different question. It's more around performance optimization and capacity planning. So RED is focused on the simple question of, are users having a good time? Right? Capacity planning is useful for, will users continue to have a good time, or how many users can have a good time? And it's important that you measure these things in different ways. People often say don't measure the mean, because the mean is not what people using your site actually experience. The 95th or 99th quantile is closer to that. But it's useful as a way to sanity check your other numbers. So we use Grafana for most of our kind of visualization stuff. Other brands are available. And we've put a lot of work into making them consistent. So QPS is always on the left, right? That's giving us the rate of requests and how many of them are errors. And latency is always on the right. That's giving us the duration, measured in 50th quantile or mean and 99th quantile. So you can kind of check things that way. This is our kind of convention, and it covers the RED 3 right off the bat. But most important, really, is making sure that things are working, up to date, consistent. Most things break because an engineer changed something, right? That is like 90+% of why things break for us. So we've open sourced a library, Grafana lib, to help with this. This is where you can get Grafana lib from. It is a Python library for building Grafana dashboards. It does what it says on the tin. It looks a bit like this. I don't really know Python that well. But it follows the Grafana dashboard JSON pretty closely. And because it's Python, you can actually define functions. So we defined one that's a QPS graph, right? And you just give it the service, it goes off, figures out how it should draw that, how it should render them to make it accurate so they're all consistent. And you can import libraries so you get the full power of Python. It's super useful, and it's about lowering cognitive load. It helps you make your dashboards consistent and manage them well so that you can have fewer people getting more done. So from each overview dashboard, we then have things structured into kind of deep dive, detailed dashboards for each service, right? So you can start at the overview, is the system healthy? And then from there you can say, which component isn't healthy, and dive down until you get a good view of what's actually broken. Just like the last one, it starts with QPS and latency. So it starts where the overview dashboard leaves off and goes from there. And then it's broken down in different ways depending on what you're monitoring. So for a lot of HTTP services, it'll be broken down by endpoint. For this one, it's doing some database storage, so it's concerned more with capacity, again, capacity planning type stuff, because that's likely where it's going to break. And it's a little thing, but one of the things Grafana does really well is they all have the same x-axis. So you can make time comparisons intuitively, easily, and kind of make assumptions about the data that actually hold up. And we think a lot of these tools help us to run fast and break things, right? Good metrics and safe tools let you do that. But more importantly, they help you fix them, right? And fix them is the more important part. And it shouldn't be scrolled in as an afterthought. When you're building the system, you need to think about how you're going to fix it. And it means learning from your mistakes so that the next time you can make a more interesting mistake. You can't fix things if you don't know they're broken, right? So we have metrics, we have safe tools, but we need a way to tell if our system is broken. And we're not going to rely on vigilance, because that's not a real plan. So we need alerts. There's kind of a Goldilocks zone of alerting. Not too fine-grained, or they'll be twitchy, but you need them to actually go off when things are broken. So how can we design good alerts? Well, first off, you should alert on symptoms, not on causes, right? It means you should be alerting on the things the user cares about. So slow page loads, for example, are a symptom that the user cares a lot about. Maybe the cause is like high CPU, maybe it's a missing node, whatever. You shouldn't be alerting on that. You should alert on that there is a slow page load. Dashboards, then, like we just saw, are how you figure out what's causing some symptom, right? They start at, the overall, is the system healthy? And then you can go from there to figure out why that symptom is happening. Your alerts should be consistent, right? You need them to be able to be compared, right? You're getting the same alert on two different systems. Are they the same thing? Maybe. But if they're consistent, you know that they mean the same thing in different contexts. Again, it's about lowering your cognitive load so that you can do more. And they should be actionable, right? You're sitting at home, 10:30 at night, you're on call, pager goes off. What does it mean? Right? They should mean that the person on call needs to do something, and it should tell them what they need to do. Maybe that's just go look at this dashboard, something's red here. That's kind of an okay minimum level, right, of what your alert should be telling somebody. And between alerts and safe tools, one of our main driving philosophies is that we optimize for mean time to recovery, not mean time between failure. That means we try to mitigate the impact of any individual failure and make it easy to fix. There's an obvious way to optimize for mean time between failure, right? Most breakages happen because an engineer changed something, so we just don't change anything, right? But that's stupid because you need to change things to make the system better. So if we have to pick, we would rather have frequent small failures than infrequent and catastrophic failures. Continuous delivery and alerting have to work hand in hand, which is where we get to our continuous delivery tool that we use. Takes a Git repo of your manifests, that's the version part, figures out what needs to change, and lets you know what it's doing. Okay, and it defaults to safe actions, so you can dry run and then release. Right, let's do a quick demo of that. Mirror displays. Oh yeah. Okay. Let's make that a little bigger. Okay, so is that big enough? That's probably okay. Cool. So this is the hosted UI. There's an open source version as well. Go check it out. So it's immediately showing me a history of what's happened. So this was actually me from yesterday deploying FLUX with itself. And it's deploying some of our Grafana stuff, so you can tell kind of how the system got to where it is. There's a kind of version-controlled service definitions of our services. So we have the billing service, we have Cortex, which is running some of our services. Let's do a deploy. So there's a service here called Pros, which I picked out beforehand. It takes some SQL queries, runs them against a database, and exposes that as a Prometheus metric. Fairly simple little microservice. And it has a newer image. It's actually the same image with a different tag. So I checked this out beforehand. Don't worry. You can relax. So let's do a release here and see what that looks like. So immediately, you can see it's doing a dry run first. So it's figuring out what would I do. Again, like Terraform helper, you should check what it's going to do, and it should make that as easy as it can. So I'm going to replace this image with this image, and I'm going to commit and push that and roll that out. Let's go for it. Live deploy from on stage. What could go wrong? Okay, so it has looked in the registry, figured out what new image do I want to release. Yep, that matches what you told me to. Updates it in the version-controlled repo, and then pushes that into Kubernetes. So it's all running. Cool. And commits and pushes everything, and we're all done. Cool. That went surprisingly well. unmirror displays again. Cool. Okay, so that was Flux. That is our kind of deployment tool. And thank you very much. Hopefully you can run fast, break things, and then fix them. May your failures be learning opportunities and your mistakes be interesting. I think we are doing pretty well on time, so we have loads of time for questions.
Anyone? So thanks for your talk. That was quite interesting because the way I understood it is that you started to build those helper tools around existing tooling in order to, the way I understand it, to somehow bring more processing into it or to safeguard the processes. So my question would be, did you look at existing tooling, how to improve and use that more? And what was the reasoning to actually build stuff yourself?
We did, yeah. So, I think I'd answer that. A lot of our process improvements, I guess as you would put them, are really stem from observing how we naturally do things, right? How do we naturally want to approach the problem, right? And then building tools to kind of push that in the right direction. There is some existing tools around that. Like I mentioned, there's a open source, newer open source version of Terraform Helper that someone else has put out. I think when we started that, that didn't exist. Yeah. I don't know if that really answers your question.
So I understand it's customizing and making it
to
your process.
Yes, exactly. Yeah. Our processes are typically somewhat different than others, which isn't necessarily a wrong thing, but it's just, people want to follow the straight and narrow path if the straight and narrow path is paved and makes sense to them.
By the way, we made the same experience with Terraform. So you need some Ansible, or some people use SourceStack. So basically, the root cause analysis was that basic operations use cases are missing in Terraform, like recoverage and like adding even nodes to the cluster. And so it's an open source tool. It does not even have a 0.1 version. So the root cause was it's like Vagrant for the clouds, and it does not really cover these cases. So everything we do is kind of workaround with Python scripts, Bash scripts, or something like that. And everybody does it. So if you roll out Kubernetes applications, be prepared to fix things in Terraform with Ansible or some other rollout tool. So Ansible preferred because you don't have to install anything on top of the machines. And other things like kubespray have the same problem. So it's 80% is working solution and 20% is spending.
Absolutely. It's still, I mean, so much of the stuff in this space is new tools, right? They are very powerful and they give you a lot of new things you can do, but there's a lot of dragons to watch out for.
Yeah, there's some room for, so I expect some tools being available hopefully this year, so this year is not so old.
Yeah.
We have good chances.
Cool. Any others? All right, one there.
Hey, thanks for the talk. Yep. And what we, for example, did, and I wanted to ask whether you did something the same. Do you have your Kubernetes files in the original version laying around, or do you have some kind of generator that kind of adds consistency checks or makes corrects namings or makes sure everything has the same name in a specific domain, stuff like that?
Cool. Okay, so.
So you do?
Yes, we do.
Nice.
So let's go back to the mirror display here, github.com. See if I can do this without leaking any secrets. Oh, my Wi-Fi's died. Okay. We do, yeah. We keep them in a repo version control, just the YAMLs right now. Different kind of folder for each environment. So there's one for dev, one for prod. We're looking at different ways of doing that. either something similar to Grafana where it's like a Python DSL that generates them for different environments. That's quite attractive because you get the full power of Python, right? Or something like a more limited DSL, maybe based on like HCL or something like that, which would be a bit more similar to like the board configuration language. And we have a couple things we've been trying around that. One of my coworkers was working on something called KubeGen that goes the more stripped down DSL route, but we're not kind of sure which way we want to go with that. I guess there's not really a agreement in people using Kubernetes that like this is the way you should do it yet. Yeah.
I have another question. If you use some validators for your provisioning, like server specs or so, if you unit test script, I think that is the missing part that I see very often in this space, that people wrote down, generate things, deploy it, and it breaks.
Yeah.
But they don't have validators in their pipelines.
Yeah. So we do some validation today. Looking at adding more, we use Circle for kind of running our CI and doing integration testing between stuff. Make sure at least the APIs, match up. Yeah.
But this is only for the automation space that you have the scenario, but which you use on validate the things.
Yeah.
Rest assured or whatever you need. I think the validation part is the hard thing.
Yeah.
I'm missing some validators for the languages that you are deployed with Kubernetes, and so they can make typos or strange things or so.
Yeah. Absolutely. Yeah. I think, again, it's still quite early in Kubernetes lifecycle. So maybe we'll see some of that come out soon.
We hope.
Yeah, hopefully. That would be nice. Cool. All right.
Okay, so one question. It's working. One question. What Kubernetes-specific problems did you run into?
Sorry?
Kubernetes-specific problems?
Kubernetes-specific problems. I want to be nice to the Kubernetes developers. How do I answer that? So personally, this does not represent the views of my employer. When we first started with Kubernetes, it was, like a year ago, so it was even earlier than it was now, right? So some of the CLI tools and stuff were really sketchy. There's quite a lot of parties involved, and they've kind of have to support quite a big API. So I know they're trying to make changes, stuff like pet sets, right? But it kind of turns into like an add-only API. So we'll see how that goes. Maybe they'll be able to simplify stuff and strip it down a little bit. That's the big problem I've seen with it. As far as actually like operating things and running, it's actually been remarkably smooth.
Did you try Helm for templating your manifests?
Tried it out briefly. I know I've talked to Remesh a bit about that. It's interesting. Don't know. Haven't tried it in anger, so that's.
I noticed in your demo you were doing a deploy, and I think you're updating your app or setting up a new app, and then you had a bunch of other containers like a Prometheus SQL exporter and some kind of Grafana thing.
Yeah.
I was just curious, how many of these monitoring containers do you typically deploy, and do you have to redeploy them every time you do an upgrade of your service, or just at the beginning? And and just what's the ecosystem of supporting containers?
So it depends on what we're actually deploying. So a lot of our Go apps typically use the Prometheus client library and just expose metrics directly themselves because it's easiest to do that way. A lot of our other apps or things that we didn't necessarily write ourselves will have a kind of sidecar deployed in the same pod with them, exposing metrics. So things like if we run a Prometheus instance itself, we'll have a exporter on itself doing that, or like SQL databases, pretty much anything that isn't a standard Go app will have a sidecar exporting that. We don't generally need to upgrade them too much. The code doesn't really change that much. When you do a release, it'll restart the pod. So it will update the pod itself and restart it in that way. So the sidecar will restart along with it. But the code doesn't really change that much because once you've got the metrics being exported, from like the metrics you get from Nginx won't really change over a given time. But it's probably just under 1-to-1 actually. Cool.
Thank you very much, Paul.
Thank you.